Hello and welcome to this lecture series on chemical process modeling and simulation. We have been building up to this particular lecture for about seven lectures so far. From 7 lectures so far, we are going to derive the three of the conservation equations in this lecture. We are going to rederive the continuity equation or the overall mass conservation equation. We are going to derive the species conservation equation. We are going to derive the momentum conservation equation. And in doing so, we are going to provide a template for deriving a general conservation equation of any conserved quantity, right, in a system where a fluid is flowing. So we started out with a model of a flowing fluid, and we looked at three different scales: length scales, molecular length scales, microscopic length scales, and macroscopic length scales. And in this, we defined a continuum model of a fluid, or we sort of proposed a continuum model of a fluid which is valid in the microscopic and macroscopic length scales. And within that continuum model of a fluid, we looked at how molecular momentum transport happens. We looked at two case studies, and then we generalized the molecular momentum transport in 3 dimensions, obtained the molecular momentum flux tensor, which also there is the shear stress tensor, which is the molecular momentum flux tensor. And then we related it to the rate of strain of the fluid due to shear or friction, and generalized Newton's law of viscosity. Then we looked at a preliminary derivation of the continuity equation, which sort of sets the ball rolling in terms of what we're going to see now in this particular lecture. And then we looked at how there are two approaches for looking at how to model a fluid flow: the Eulerian perspective and the Lagrangian perspective. The Eulerian being the fixed coordinate system perspective, Lagrangian being the moving coordinate system perspective, where you are moving along with the fluid, right? And then we related these two, and then we looked at convective momentum flux tensor. So we looked at how to account for the momentum flux due to bulk flow, convection, right? So now that we have done both the molecular momentum transport, the flux corresponding to it, and the bulk or convective momentum transport, the flux corresponding to that, all right, we are now ready to take the picture that we sort of created in deriving the continuity equation and sort of generalize it to momentum conservation equation. So that is what we are going to try to do. We are going to create a general template for deriving the various conservation equations. So this is a general conservation equation. How does it look? What are all the pieces that a general conservation equation has? And that's something that we're going to see now first. With the background so far in momentum transport, we now present a general approach to deriving equation of conservation of any quantity. Then we will use it for momentum conservation. Now again, we have an arbitrary control volume V, which is covered by a simple surface. All right. So, and we are looking at some arbitrarily general conserved quantity f of t and a time independent control volume V, in which it is conserved. Let A be the time independent boundary that encloses V. Now we are going to look at the first thing which we looked at also when we derived continuity equation, which is the flux of this quantity through the surface. Let the surface flux of the conserved quantity be phi f, and at any point the surface is defined by the outward normal vector. So the outflow of f through that point is given by n dot phi f. Now then there is the other quantity that we are going to define, which is let SF be the rate of production of this quantity within this volume, all right? So within this particular volume, what is the rate at which this quantity is produced by an externally induced force. For example, momentum is produced in a quantity by gravity, right? And this causes motion of that quantity, of that object, bulk motion of that object, right, subject to gravity, isn't it? So this kind of production, the rate of production is given by SF within the unit volume, right? The surface flux is given by phi f. Now, the small f, what is the small f? Small f is the general conserved quantity per unit volume. So how do we get capital F from small f? You integrate the small f over the entire volume. So you do a volume integral and that gives you the capital F. So this is like saying if f were mass, small f would be density, mass per unit volume. If f were momentum, m into v, small f would be rho into v, which is density into velocity. So that would be momentum per unit volume. So this, I believe, if you recall, in one of the early lectures, we defined these quantities per unit volume and that they are corresponding fluxes, right? If you recall, there was a table that was provided, right? So we can use that to relate to these quantities here, small f and capital F. Now, in thermodynamics, this capital F is an extensive quantity, while small f is the corresponding intensive quantity. These are terms that are commonly used in thermodynamics parlance. So, as I said, capital F of T is integral over the volume, control volume of small f of x comma t over the entire volume. So what causes df by dt? What causes rate of change of this quantity that is conserved, right? So first thing is the efflux, or the flow of this quantity out of this control volume through the surface A, and that is one that causes the rate of change of F. In the case of overall mass, when we derived the continuity equation, there were no other sources or sinks for overall mass, and therefore this was the only quantity we had to consider. So then we essentially wrote that this change is due to the efflux, and we derived the continuity equation. Now additionally, you can have local sources of F, which is from the sources or sinks from within. Alright, so example, homogeneous chemical reactions which produce product species and consume reactant species. So these homogeneous chemical reactions are sources for product species and sinks for the reactant species. Suppose some reactant A gives B, alright. So a reaction, homogeneous chemical reaction, will be a sink for A and a source for B. And now the next thing is the externally induced sources of F, which is given by your small sf. As we discussed, gravitational force is an externally induced source of momentum, right? Bulk momentum. So if I were to, here this is the key thing. So df by dt is given by the integral over volume of dou f by dou t and dv. This is the key expression that is important in obtaining your conservation equation, right? So since f is integral, capital F is integral over the volume of small f. Now if I were to figure out what is the overall rate of change of mass, for example, that is integral over the volume of the rate of change of density at every point. So when I say that I integrate the rate of change of density at every point over the entire volume, now I am getting the rate of change of mass in the entire control volume. This is caused by net flux out of the surface, which is given by the surface integral n dot phi f dA, n being the outward normal of that indicates the curvature of the surface at any point, and then you look at the dot product with respect to the flux, okay, phi f. Since n is directed outward, you have a negative sign. Local sources of f, so you integrate over the volume eta f, and externally induced sources of f you integrate over the volume sf. Thus the conservation equation is simply given by dou f by dou t integrated over the entire volume is given by the surface integral, the flux dot product with the x outward normal. This is the net flux, and then this is the local sources and external sources put together in the volume. Now this term, as you notice, is the only extra term that comes up compared to what we did when we derived the continuity equation. It is to be expected because there is neither a local source nor an externally induced source of mass, overall mass, in a non-quantum, in a non-fission, non-fusion kind of a process. And therefore these two terms were all that were there in the conservation equation, continuity equation, which is the conservation of overall mass. Now here in a general conservation equation, you have these two additional terms that get added. That's it. Using Gauss divergence theorem, then I convert the surface integral into a volume integral, where I get the divergence of phi f, and then so I combine these terms, all right, into one particular integrand. Since this is valid for any arbitrary volume, so I can take on both sides the limit of v tending to 0, and this will give me dou f dou t is minus del dot phi f plus eta f plus sf. This is basically my general conservation equation. Now let us try and apply this to continuity equation or the overall conservation of mass. For overall mass, small f is mass of the overall fluid per unit volume, which is the density. Species flux phi f is equal to rho into v. There is neither local source nor external source for overall mass. So eta f is 0, sf is 0. So the general conservation equation becomes, this is your general conservation equation. The last two terms are going to go to 0. This is going to be del dot rho v, and f is going to be rho. So that is your conservation equation. This is your continuity. Now, if you were to look at the component continuity equation or the conservation of species, for any species I, f is the density of that particular species per unit volume, that is given by rho I. Now, if this density were a molar density, this would be Ci, and would be concentration, all right, of that particular species, number of moles per unit volume, number of moles of that species per unit volume. The species flux is rho I Vi. This again you have learned in your mass transfer course. Suppose there are n components, sum over all the n components will give sigma rho I Vi will be rho v, right? So where v is the mass average velocity. This is something that you have learned again in your mass transfer course. So the difference between the v and the Vi defines the diffusion flux, such that the net diffusive flux is 0. So sigma iji is 0. This is familiar to you. Now, if you are looking at species, what is the rate of generation of species, and is given the local source for the species. The generation or consumption is through some homogeneous reaction, and the rate of that particular reaction is given by r dot I. Just write a rate equation, first order, zeroth order, second order, or any complex non-elementary kinetics that you have, or elementary kinetics that you have. So basically this gives you eta f is this simply this Ra dot, and then phi f is rho I vi, which is your species flux, which then can be split into two parts. One is the rho IV, which is the convective flux, and then the second is the Ji, which is the diffusive flux. This is how the convective and diffusive flux sum up together to get the overall flux of that particular species I. There is no externally induced source for species. You cannot suddenly generate a species from an externally induced source. So SF is 0. Thus the species conservation equation is then given by, then you have this overall conservation equation, which is dou f dou t is minus del dot phi f plus eta f plus sf. Phi f is then replaced by rho I vi, which can then be split into these two, and then eta f is replaced by Ra dot and sf is 0. So then you have two divergence terms. One term is that of the convective flux, the other term is the diffusive flux, and then you have the reaction term. So if you were to, this is in the Eulerian formulation. In the Lagrangian formulation, you as you know, your d rho I dt, the d by dt that is with the capital D, it is dou t plus del dot the quantity into V. So basically this together is your the substantial derivative of the density of that particular species, or the concentration of that particular species. Then on the right hand side, then you have only the diffusive flux and the homogeneous reaction term. If you sum over all these components, then this term will vanish. The net diffusive flux will be 0, and then all this will vanish. So if you have converted one species into another, all of them will, whatever has been lost for one species will be gained for another species. All of this will vanish, and then these two terms will essentially sum up to your continuity equation. So this is your species conservation equation. Now the conservation of momentum, this is the next thing that we have, Euler equation and Navier-Stokes equation. Now again, if you consider this control volume, the small f is momentum per unit volume, which is rho v. Capital F is momentum, of course. Again, your momentum flux will be convective momentum flux plus molecular momentum flux. Convective momentum flux is rho vv. Molecular momentum flux is the pi tensor that we had. So this has the pressure term and this has the shear terms. Normal pressure, which is P into I is the identity matrix, and then it's a unit tensor, and then tangential shear. So therefore your phi f is rho vv plus pi, which is rho vv plus pi plus tau. This is what is your phi f, which is your momentum flux. There are three components, one being the convective momentum flux, one due to pressure, one due to shear, right? There is no local source of momentum or sink of momentum. There is no reaction or some kind of quantity that can suddenly generate momentum from within. There is externally induced source of momentum, which is due to the body force, for example, gravity. So this external source of momentum will impart momentum to the entire body. There is no individual molecular selective imparting of the momentum. Therefore, the body force is given per unit volume, of course, is given by rho g. Then the conservation of momentum. So you have these terms. All right, dou f dou t is minus del dot phi f plus eta f plus sf. Now your eta f is 0, sf is rho g. And this has three terms: convective momentum flux tensor, then you have the pressure, which is an isotropic unit tensor multiplied by P, and the third is the tangential shear stress tensor. So then you have these three quantities that show up. Okay, so then you rearrange these, so you get, this is your substantial derivative again, all right, and this is your pressure term, this is your shear term, and that is your gravity or your body force term. So this is d by dt of rho v, which is your momentum per unit volume, and then there are three sources for this, essentially three causes for change of this momentum per unit volume. So on the left hand side, if you look at it, what is this? This is the rate of change of momentum per unit volume of a fluid particle. If you are sitting along the fluid particle and you are moving along that particle, this is the rate of change of momentum per unit volume. This is basically density into acceleration. If your density is constant with respect to time, you can take it out, all right, and then you will have dv dt, which is acceleration for an incompressible fluid. This is from a Lagrangian perspective. These three together give the net force per unit volume acting on the fluid particle, body force and the two surface forces. One is the frictional force, the other is the pressure force, and the third is the body force here, which is the gravitational force. So this is basically Newton's law of motion for a fluid looked at from a Lagrangian perspective. This is essentially density into acceleration. So this is, you know, net acceleration in times mass per unit volume. These three are force per unit volume, net force sigma f per unit volume. So with that, we come to the end of this particular lecture. There is just one point that I would like to make, is that in this lecture, in this deriving this momentum conservation equation, I have not introduced the Newton's law of viscosity for shear stress. So this equation of motion is called the Euler's equation of motion. Now if you introduce the Newton's law of viscosity into this momentum conservation equation, then the resultant equation is called Navier-Stokes equations, right? So this basically is the conservation of momentum for a flowing fluid. All right. So thank you for listening to this lecture. If you have any questions, you please feel free to post them either on the YouTube channel, or you can write to me. I'll be very happy to answer your questions. Thank you again, once again. You have a wonderful day. Thanks.